Hi, good morning, and welcome to the ZP Developer Zone. We do this webinar for the members of our Developer Zone every Thursday at 8 a.m. London time, and I will essentially sort of jump straight into it. So the first thing I want to do today is really discuss. And I'm just going to resize something because I realize this. I just want to discuss what we talk about every week in the developer zone, which is, we have our ZP Academy, and our ZP Academy is probably pertinent to today's conversation. The ZP Academy is the sort of free courses that we do for people who want to learn about electrochemistry. I'll go a bit quicker because we do have a lot to cover today. We do have our webinars. We do these webinars, for example, every Thursday at 8 a.m. London time. We have our collaborations. We mentioned that, we have our ZP Developer Zone member from Turkey over at the moment. We promote jobs, and we have our ZP Developer Zone website and forum. So I'll go a little bit quicker. And we're also doing a workshop. We do have a workshop planned for Norway, and it's probably worth mentioning that we actually in India we're represented by Technando. It's just come to me at the moment, but we are planning a trip to India in what we call Q3, quarter 3 this year, and it's probably, if you're interested in a let's say a ZP workshop, then I think we'll end up doing one in India, so that needs to be discussed and planned, but just to sort of comment. So we got 3 questions. Question number 1, we have an inquirer who wants to know about pH, calcium and phosphate sensing. I'll go a bit faster. Question number 2 is about making glucose and lactate sensors using nanoparticles, and question number 3 was measuring chlorides. Number 3 is almost the hardest one. It came in rather late, let's say last night, and I still have to get my head around some of the nuances of the question. If I go a little bit quicker, the first question was they would like to measure pH, calcium and phosphate in solution. They would like to do it in SPF, which is this simulated body fluid. They want to know how long can the devices be used after a long experiment. The answer is the pH sensors that we have a lot of history with those, and so we I can have some good confidence in those sensors. The calcium and the phosphate, we don't have a lot of data in terms of long-term experimentation, so that one I really, has to be tried, I would say. They say here for the pH sensing, that they want to measure between 1 and 14, which is really quite extreme, but it's okay. I say it's okay. I mean, I think we measure typically between 2 and 10. So I can't say about between 1 and 14. I think if you look at the online data we have for the pH sensor, then we have 2 to 10. It says here, what's the minimum concentration that can be detected? It's a good question, actually, but I think we've got it on our... I'll point out where we have the data on our website. And obviously with pH is a funny question when because obviously, we measure pH 2 to 10, which is sort of 10 to the minus 2, 10 to minus 14. So I could answer the question, I think we sort of measure 10 to minus 14 molar on pH, which is quite, low. But, sometimes these questions are, it's hard to answer them. But we do have the data on the website, so I think you have to check what data we have. They do say here that we have a rather large device, so I'm not going to suggest a large device. So I'm going to go a little bit faster now, which is we have our pH sensor, we have our calcium sensor, and we have our phosphate sensor. So these do obviously exist. And I would say start simple. And what I mean by start simple is just start with one of these things. When you start with 3 sensors, you know, you're starting with 3 things to optimize and 3 things to troubleshoot. So my I just want to say hi, good morning to Aftab. Good morning to see you. Nice to see you, Aftab. So start simple. Just start with the pH. The pH is the sensor we've been making the longest. It's the most robust. You know, so I would actually start with the pH. So start simple. You can add the other ones later on. Now, I did say earlier on that, you know, we do have data, so you can look at our pH data, and I'll try and put these links under the video afterwards. You can also have a look at our calcium data, and you can also have a look at our phosphate data. That might help answer that question, what's our sort of limit of detection. And I say that because I realized that I haven't actually addressed our limit of detection in these. But so far I've said we have all 3 sensors. They're all ion selective electrodes. The pH is the one that we sort of manufacture in the highest volumes and is the one that actually, you know, you could sort of reuse and reuse. So I'd actually start with that before I start getting into calcium and phosphate. Now, how to bring the sample to the sensor, that's a tricky one. So here I've done sort of, you know, 4 modes. Mode 1, you bring the sample to the sensor. Mode 2, you did mention wanting to measure these things in parallel. This is still bringing the sample to the sensor, but it's doing it in parallel. I've got a video on that. Mode 3 is the one I think you should be trying, which is when you know, start off simple. So I would almost say, you know, start with a beaker, put the solution in there, put the pH sensor in there, and just measure it. And I will talk about the kind of materials that we have to do that. Mode 4, we have our more complicated workflow with sensors, pumps, valves, and I'll discuss that as well. Right, so the question was, I want to measure pH, calcium, and phosphate, and I'm saying, right, start off simple, start off with just pH. Mode 1 is the simplest one. You just have essentially a sensor, you put a sample on there, sensor sits in a meter. This is the way we do it. This is the way we do it. This is the way, you know, and we send the data via an app to our database called Julie. Now, the thing is, you don't want to do that. I think you want to do continuous measurements. So mode 1 is not really an option for you, but mode 1 is one of the simplest things to do. Mode 2, you know, just skipping through options. But again, mode 2 is something that we do develop for people. And it does answer the question, can I have sensors, you know, essentially in parallel or in a single piece? You can. This is, you know, one way that, you know, this looks like a concept, but it's actually something that we've done, you know, where we can have several sensors in the same cartridge, and we can bring all the samples. Well, we can bring one sample up to several sensors just by splitting the flow. Again, I don't think mode 2 is going to work for you because I think you want to do continuous measurement. So mode 3, we have something called the application zone. I've got a link here. I'll try and put that link underneath the video as well. In the application zone, there's lots of demos of us using our biosensors, and I think there's a particular demo. This one's a good example where we're doing what I call a beaker experiment. So mode 3 is a sort of beaker experiment where, you know, you have a beaker with a solution in it, and you literally just dip the sensor in like that. So I'd almost say start off simple. In fact, do the experiment like this. You know, just try it, because the biggest step is actually trying it. So get some pH sensors and just put a sensor in there and sort of put your calcium phosphate and your pH solutions in there and just start seeing what you get. So the way that when I say the way that Yaron sets up the experiment here, it's not the way she set up the software, it's the way she set up the actual experiment, where she essentially has the sensor in a beaker. That's the sort of simplest way to essentially get going with this. One of the lowest cost options on electronics is something that we call the ISC OEM solution. The nice thing about it is there is a video on the page that I'm going to link to, which will actually the video is made by one of our other engineers, Solrun, and you can see there that I think it's about 250 euros for this particular electronics, so it's quite low cost. So I think if I was to summarize it, I've still got, yeah, mode 4. So mode 4 is the most complicated way of doing it, but this can be done. We have done similar things to this. It's a bit of an engineering project. That's the only thing about it. So we have our sample. So let's say you're doing some sort of bone growth, because you had pH, calcium, and phosphate, and you were doing some sort of bone growth. So essentially, you've got a reaction going on. You have a pump, and the pump is, for example, a syringe pump, and it's actually pulling samples from the reactor. I prefer mode 3 because in mode 3 you've actually had the sensor in the sample at all times, but there's a problem which I will bring up. But mode 4 overcomes the problem. So you have a sample or the reaction going on. You pull samples out of the reaction using something like a syringe pump, and you pump it over a flow cell here. We do have flow cells. If you Google Zimmer P got flow cells, you'll start finding this kind of thing. And we have a switchable valve. Now the switchable valve allows you to pull from the sample or to pull from calibration solutions. And the reason I bring that up is because there's one thing that sensors do, or biosensors do, is they drift. So the perfect signal is if the pH, for example, is stable, then obviously the signal is stable. But anyone who's used a pH sensor in the lab, you know how often you're recalibrating them every time you use them. And it's because sensors drift. So the reality is sensors do this. When you have calibration solutions, like as I've shown here, you can actually run calibration solutions periodically over the sensor and do a recalibration. What I'm describing here is the workflow for a product. And that's sometimes the problem. That's, the sort of desire you might have. You're really saying, I want to develop a product. So for me, mode 3 is the simplest one to do, but the only issue is drift. And the reason I'm a bit hesitant is because whether or not you have drift and the extent to which you have drift is really dependent on the experiment. See, biosensors and chemical sensors are different from things like temperature sensors. And it's taken me a while to understand why this is. It's because the sensor, as you can understand, is inherently in contact with the sample. A temperature sensor is actually, the temperature is sensing part itself is not always, but often isolated from the sample. But in biosensing, you are in contact with that sample, so you're in the experiment, and things can absorb or desorb onto the surface of the electrodes and cause you problems. So I bring up mode 4 because my biggest concern is you're going to have drift. If my recommendation would be to actually run in mode 3, do some benchtop experiments in mode 3, and then understand what that drift looks like. If you've got it, you've got it, and you might have to, unfortunately, then go to mode 4. Well, unfortunately, mode 4 is quite a it's a lot more purchase of equipment. You have to set it up, you have to tune it, you have to optimize it. You're essentially trying to make a product at this point. So if I was to summarize it, I would say use the techniques of that, or use the setup that Yaron is using. So we have something called the knowledge base. I'll try and put a link underneath the video. The way she physically does the experiments. I say that because she was actually running a amperometric experiment there, but you need to be doing a potentiometric experiment. And maybe if you want some low-cost electronics, then you can take a look at this OEM solution that we have, and I'll try and put some links also again underneath the video. All right, so it's 8:15. Question number 2. Somebody's trying to work on making a glucose and a lactate sensor, and they want to do it by patterning with nanoparticles. Okay. All right, so we'll address that. So first of all, I think it's just worth diving into and having a look at our glucose and lactate sensor, because that's going to give you a little clue. And the little clue is, when you look at what we have, you'll notice the geometry of the electrodes. There's a big thing in academia that people essentially want circular electrodes, we often recommend these rectangular electrodes. I will discuss why that is in a minute. But there's a bit of a clue that actually we like to use these rectangular electrodes when making glucose and lactate sensors. If you want to see what we have, take a look at that. These links, at least it'll give you a reference point so that you can compare what you're doing to what we're doing. It's probably worth noting actually that these signals, people are sometimes worried that, you know, these smaller electrodes won't give you strong signal. We've got strong signal here. Yeah, 0 millimolar glucose and 5, 10, 15, 20. They're very clear signals, so I won't worry about signal strength too much. I know lots of people are very interested in these sort of circular electrodes, and I have a little article online that was sort of basically talks about what's wrong with screen printed electrodes, or what's wrong with R&D screen printed electrodes. So I do think it's worth taking a read on that, because one of the first problems is, this is ironic, but actually this is a manufactured project by Zimmer and Peacock, and I'm criticizing it or critiquing it on our own website, and I criticize it because obviously, having manufactured these, you know, you learn a lot, and what you learn is that these traditional R&D electrodes that people like, they're too big. And what I mean by too big is, you know, for me, if you're making a glucose and lactate sensor, it's an R&D effort, but clearly, you know, you've got a commercial, you know, you want to make, you're making something that's commercially interesting. I mean, both glucose and lactate are very commercially interesting. So you should start on a platform that at least stands a chance of becoming a low-cost biosensor at the end of it. So even though we manufacture this, and I've put a link to it here, you can buy a pack of 50. I would say before you start jumping onto something like that circular electrode, do read the article. Of course, then at that point, you know, people are of course free to, you know, make a decision. People like it because they like the fact that you can sort of pipette into the middle of it like that, and, you know, sort of drop spreads out, and they find it very easy to fabricate with. In the article, I do discuss, you know, that, you know, we understand why that is, but we also understand that, you know, that geometry is not good for flow channels later on. So that's one of the points that should be read in that particular article. Now, what I'm, you know, always recommended is these hyper value screen printed electrodes. I'm just remembering I've actually got a big meeting today about hyper value screen printed electrodes, because, you know, they're one of the things that we manufacture a lot of. So myself and my business partner and our operations guys will get together today to have a big discussion about these. Anyway, that's a side point. I recommend the hyper value carbon electrodes. It's just so simple. I mean, in its simplest, you know, we sell it in lots of ways, but it's 145 euros for 300 electrodes. It just allows you to make lots and lots of mistakes and do lots and lots of optimization, and it doesn't cost you lots and lots of money. And they are high quality. Why they're high quality? Aftab, who's online this morning, knows why I say this, because we use these electrodes day in, day out, which means that we're producing a lot of them, and then, you know, on occasions we have to produce even more of them. But I would go that in this direction. It's so low cost, and it's got the quality because we're the biggest users of these electrodes. They're easy to functionalize. I've mentioned it in the past. You just put 3 drops like that, they'll coalesce, and you functionalize the electrode. Now, people are concerned, well, you know, the electrode's too small. It's not too small. This is a gold electrode in the same geometry. We're using it here in an immunoassay, and we're able to get electrochemical signals out of this when we're testing at like 5 nanograms per milliliter, 25 nanograms, 50 nanograms per milliliter, 75 nanograms per milliliter. So please read the article on what's wrong with R&D screen printed electrodes. You can use those disc electrodes. We do, you know, I will put a link to the gold ones underneath this video. My recommendation is use the hypervalue carbon electrodes. The carbon will give you essentially the substrate which your particles can go upon, and give you electrical contact. And then you can optimize. You know, if you make a mistake, it doesn't matter. It costs you less than 50 cents. When you're making a mistake on ceramic or larger electrodes, you know, it's a couple of euros, which is okay, but it soon builds up, and you get complaints from your principal investigator. So in summary, you can use these gold ones, for example. I would rate these, and here's some links to those. I'll tick. Question number 3 is almost the hardest question. It came through last night. I will go pretty fast. Right, we are using cyclic voltammetry to perform chloride measurements. That's intriguing in itself, because if I was making a chloride sensor, I would be using ion selective electrode techniques and open circuit potential. Anyway, they changed the chloride concentration from 10 to 70 millimolar. So after 2 to 3 runs, the non-Faradaic current in the CV was increasing with the same chloride concentration. So it seems to me they're doing subsequent experiments and the non-Faradaic region on the voltammetry was increasing. First of all, we've got to make sure we understand what... some data came through as well. And the reason I bring this up is because it's not clear to me from the data. The units are not shown here. So I was thinking, is this current? But actually, I think in the end it's voltage. And again, it's not shown here. In fact, now I'm realizing, you know, this might be current and this might be time. It's really not sure. So unfortunately, with the data, sometimes we need the axes because they talk about voltammetry. So then I would guess that's 0 to 500 millivolts, and therefore that's current. But it's not absolutely certain to me whether we're looking at time, or time and voltage, or voltage and current. But let me get back to the question, which is they're interested in the non-Faradaic region. So first of all, we just have to kind of understand what they're meaning to there. So I think what they mean there is this region here. If I was doing a voltammogram, there's a region before my sort of my wave or my peak, and it's that region. And we have discussed this in videos before. So we have all these other regions, let's say, and that's covered in a video, which I'll also put a link to. But I'll go back and just say, all right. So I'm thinking that they're saying that I'm having increasing current in my non-Faradaic region every time I do a voltammogram. We don't absolutely know how they're doing the voltammetry, but if they're using a hypervalue carbon electrode, then they have a carbon working electrode, a reference that is, that's voltage, okay. It's OCP, okay. Right, so I've just had a clarification online that this data is OCP, so I'll go back to that in a minute. First of all, they're doing an experiment, and every time they do an experiment, the non-Faradaic current is increasing. Now, I think they just have chloride in PCB, in printed, PBS, phosphate buffer saline. What it's telling me is that there's nothing, let's say, very electrochemically active in that. Now, what do I mean by that is this, that chloride could be oxidized to chlorine. But not at the kind of, I doubt they're going to those kind of voltages, but I don't know what voltages they're going to. I would say that if your non-Faradaic region is changing in voltammetry with successive voltammetries, it's probably because you're somehow altering the interfacial region every time you do a voltammogram. So you do a voltammogram, you go to a voltage, you're essentially changing the electrode every time. I mean, this is okay. I mean, screen printed electrodes, you know, they're originally used for making glucose sensors. You know, you do a reading, you get the result, goodbye, the sensor's thrown away. So this, within the idea that that's what screen printed electrodes were first intended for, you know, you use them once, you throw them, then those changes, let's say, wouldn't even show up. Now, back to the question is that they have a carbon working electrode, and it's probably being changed during the voltammetry, and I think it's because, you know, you're applying essentially a voltage to it. You're possibly oxidizing the carbon, and it's changing. But is it really a problem is the question, because I do find it unusual that you would try to measure chloride by voltammetry. There's sort of, it's interesting, but I can't really see the mechanism for it. So my answer is yes. In the non-Faradaic region, it probably is changing after every voltammogram. I found it interesting that when you used other ferrocyanide, maybe it didn't change, but I probably need, I probably am not surprised, and I don't think it's really necessarily a problem you have to fix. There's a sort of another bit to it which says we ran control with phosphate buffer and Fe2 plus Fe3 plus, where it's not showing this problem. See, so it tells me, you know, the clue here is when you have electrochemically active molecules, you're getting results that you feel, you know, are okay. But when you don't have electrochemically active molecules in the solution, then you're getting results that you find strange. So the techniques of voltammetry, are sort of, designed to do electrochemistry. So when you do leave out an electrochemically active molecule and you get sort of results that you find strange, it's because you're not really doing, there's nothing electrochemically active in there. I find it nice that you're telling me that, when you use ferrocyanide, the system behaves itself. So, because intrinsically, ferrocyanides are electrochemically active, and so you get, classic results. When you've just got nothing in there and it's just chloride, which is not necessarily electrochemically active, then you get results that you find odd. But you're trying to essentially do an electrochemical experiment on something that's not electrochemically active. So I sort of, it's not the experiment I would have done. And I wonder why to do the voltammetry on chloride and look in the non-Faradaic region. If it's changing, it's probably because the electrode is changing with each voltammogram. If you wanted to reverse it, you've probably, if you're doing a voltammogram in a positive direction, then you could probably hold something like a negative voltage on it to sort of reduce the surface back. But I wouldn't really worry about it too much. I'm not quite sure why voltammetry on chloride solutions, I must admit. I'll jump to the second question now. Right. There is noise in the open circuit potential. This now I understand, because in real time, AFTAB has been updating me. So what I'm looking at here is, I'm just checking. Yeah, it's OCP data. So that's voltage and that is time, which is completely fine, because when I look at this is 314 millivolts here and 318 millivolts here. So this entire scale is 4 millivolts. Don't forget, that when we're doing open circuit potential type experiments, we'll do a pH from 9 to 10. So from a pH of 9 to 10, we'll have a signal jump of 59 millivolts. 59 and so this is really down in the noise of what we would be doing. This is 4 millivolts. The entire scale here is 4 millivolts. It's like zooming in. You've got basically essentially no signal. You've zoomed really deeply in, and now you can sort of see the intrinsic noise of the signal. This noise on this scale is sub milliamps, so millivolts of signal. The entire scale is 4 millivolts. So this, is possibly, I'm sort of guessing a little bit, but 0.00 millivolt type stuff. So it's really, I would say of no issue. You've just zoomed in a lot. I just want to read something that AFTAB is writing. Yeah, exactly. Yeah. What AFTAB is saying is the same as me. See, if you're going to do voltammetry, you need redox molecules in there in order to do voltammetry on. So when you just have chloride but no Fe2 plus Fe3 plus, there's no redox going on there. And now on question 2, they're worried about the noise, but it's like any signal. If you zoom in really deeply, you'll probably see some like inherent noise. But the signal in OCP type experiments, is for us at ZP, is often in the 59 millivolts type. We'll get a difference of 59 millivolts. Here we're looking at a scale on a difference of 4 millivolts. I just think it's just too zoomed in, and it's not really a problem. It's just you need to zoom out a bit, and it'll just look like a straight line. And it's probably worth saying that when sharing data with us, it's probably worth getting people now to open up accounts on Julie, upload their data and share their data. It just gives us, gets us into the habit of using Julie. So Julie is an online database. We want to use it with collaborators and questioners. You can upload your data, share your data. So that's a good way, because that will then help answer questions like what's the axes when receiving data. So there's an awful lot there. I can see it's 8:29 in London here, so I better be quick. Question number 1, pH, calcium and phosphate. Start off simple. Just work on pH. There's almost like a master's worth just doing pH. It's a PhD's worth to do pH, calcium and phosphate, and it'll take a while to kind of tune everything in. Glucose and lactate. You can use the disc electrodes. I have shown you that actually these kind of rectangular small electrodes, we use them to make immunosensors. They work perfectly fine. We use the rectangular electrodes to make glucose and lactate sensors. They work perfectly fine. I like the price point. You can make a lot of mistakes and nobody's going to worry about the budget. On the first one, there was a question about. On question number 3, there was a question about why does our non-Faraday region change with each cycle of voltammogram. It possibly does. I don't think it's a big issue, and if the issue goes away when you put some redox active molecules in there, then it tells you that voltammetry is a good technique when using redox active molecules, and maybe you just get sort of spurious results when you don't have a redox active molecule in there. Regards to the open circuit potential, I think you were just so zoomed in. You could see some sort of intrinsic noise, but your entire scale was 4 millivolts. Your kind of noise was sub millivolts, and I would expect, a pH sensor, pH 7 to 8, you get a change of 59 millivolts, and so you're so zoomed in, you're just seeing essentially the baseline and some noise on it. It's 8:31, so I better say thank you to AFTAB, thank you for all the questions this week. It felt like it was going to be an easy week, but it got quite heavy at the end. All right, so take care, and we'll be doing this again next Thursday.